Hello everyone, my name is Kenta Murakami. Thank you for your coming on my presentation. I am a member of Panasonic Automotive Systems Company. I'd like to talk about achieving a software-defined multi-display system with Unified HMI. Okay, this is my first time presenting at the AGL meeting, so I'd like to introduce myself briefly. I'm working for Panasonic Automotive Systems for 2 years, and I'm focusing on graphic-related development, and especially display virtualization across multi-display. I like to travel and enjoy coffee and ramen and other delicious food. I took all these pictures in various places in Japan, so if you're interested in this place, please ask me anything. Okay. Before I start my presentation, I will introduce previous presentations about Unified HMI in past AGL meetings. Our company, Panasonic, have introduced the overview of Unified HMI at Mizuyama-san's keynote in 2020 and yesterday's Mizuyama-san's keynote or Jerry-san's SDB Easy sessions. Last month, we committed some of the features of Unified HMI to AGL UCB. Today, I will talk more detailed technology of Unified HMI and how to use Unified HMI committed to AGL UCB. So by listening to this presentation, you can easily try using some of the features of Unified HMI committed to AGL UCB. Okay, let's start my presentation. Agenda is as follows. In the first section, I will provide why automotive industries needs Unified HMI. And first, please watch the Unified HMI concept demo video.
Unified HMI is an open-source display virtualization technology developed by Panasonic. In this demo, we will show how Unified HMI enables to design and develop entire cockpit UI and UX efficiently across multiple displays without dependency on hardware. Here is a cockpit UI and UX development environment that virtualizes the physical automotive environment. For example, this environment virtualizes a cockpit consisting of AGL and 2 Yocto Linux to evaluate the cockpit UI and UX across multiple displays. This is a Unified HMI associated layout design tool. It enables to develop cockpit UI and UX across multiple displays in the virtual environment. Take this sample graphic application of the Linux Penguin as an example. If you want to change layout of it, you can flexibly move and rescale the application across multiple displays. You can even design across-display animations. Once the layout design is complete, you can easily verify the entire cockpit UI and UX in the virtual cabin environment. Now, you can see the designed animation across multiple displays and operating systems. Last, after verification in the cloud virtual environment, the developed cockpit UI and UX can be seamlessly deployed to the physical ECUs with same binary. In this way, Unified HMI enables to efficiently develop entire cockpit UI and UX by anyone, from anywhere, without dependency on physical automotive hardware. Therefore, it greatly contributed to reducing lead time and costs of entire cockpit UI and UX development.
Okay, thank you for your watching, and sorry for my sound trouble. Okay, in this video, there was an introduction about layout design tool, but it is just a support tool and not Unified HMI's main technology. So I will not provide details in this presentation, sorry. Okay, next, I will introduce trends in the automotive industry. In recent years, the number of in-vehicle displays has been increasing, especially in high-end vehicles. For example, the appearance of head-up displays and camera monitoring systems, and the digitization of information displays such as meters. This has led to focus on flexible application layout, display technologies across multiple displays. And these technologies are expected to provide new UI and UX possibilities. However, if we want to develop this flexibility using existing graphic framework, ad hoc interoperability development of displays for each hardware platform is required, and it is very costly and time-consuming. Therefore, there are needs in automotive industry for a software-defined display framework that separates software from hardware. Okay. We Panasonic developed a software-defined display virtualization platform based on Volatile GPU called Unified HMI. And Unified HMI allows for flexible development of the entire cockpit and cabin UI and UX across multiple displays, independent of hardware and OS configurations. The entire cockpit UI and UX is developed using virtual environment, and it can be seamlessly deployed to the physical environment. Let me introduce some values that Unified HMI can provide for both automotive developers and automotive users. First, automotive developers will be able to agile and software-defined cockpit UI and UX development. Specifically, Unified HMI enables efficient and integrated cockpit UI and UX development and evaluation across multiple displays on virtual environment, independent of hardware from software, and scalable to deploy seamlessly to various car grades and models. Second, automotive users can experience fast and personalized evaluation with cockpit UI and UX. Specifically, users can receive upgraded customer experience from frequent on-the-air upgrades on UI and UX improvements. In addition, flexible cockpit UI and UX able to be customized according to user preference, no matter of car grades and models. Unified HMI provide value mostly for automotive developers, but efficient development using Unified HMI leads to UI and UX experience which meets user preference, and it provides a very big value for automotive users. Next section, I will provide a technical overview of Unified HMI. Unified HMI consists of two main components. The first component is Remote Bus I/O GPU. We call this RVGPU. It is shown in green box in the below figure. We recently committed this RVGPU to AGL UCB as a part of Unified HMI technologies. RVGPU can render applications remotely in different SoCs or virtual machines via network. The second component is Distributed Display Framework. It is shown in yellow box in this figure. This distributed display framework allows flexible layout control of applications across multiple displays. In summary, distributed display framework determines the layout of applications across multiple displays, and RVGPU render applications remotely in different SoCs or virtual machines as needed. Thanks to this system, Unified HMI allows for flexible development of the entire cockpit UI and UX across multiple displays, independent of hardware and OS configurations. The following describe these two components in detail. First is RBGPU. RBGPU is a network extension of VAT-IO GPU, commonly used for GPU virtualization in virtual machines. RBGPU can be further divided into two main components: RBGPU proxy presents on the left side and RBGPU renderer presents on the right two box. RBGPU proxy transfers GPU commands generated by OpenGL ES to other SoCs or virtual machines. And RBGPU renderer receives GPU commands transferred by RBGPU proxy and renders applications graphics using that commands. RBGPU also creates virtual input devices such as mouse, touch, and keyboard using U-input device. If you touch remote display, input events can be sent to applications via U-input devices created by RBGPU. Next is distributed display framework. As shown in the below figure, distributed display framework maps multiple cockpit physical displays into a single large virtual screen. By placing applications on the virtual screen, you can control the layout of applications across multiple displays. Distributed display framework allows developers to control layout such as placement, size, and display order of multiple applications. If applications are placed across multiple displays on the virtual screen, RBGPU renders those applications remotely in the corresponding SoCs or virtual machines. Next section, I will provide the past and future Unified HMI's contributions to AGL UCB. Last month, we committed RBGPU, shown in the green box, specific usage of the committed RBGPU on AGL. Will be introduced in the next section. In the future plan, distributed display framework, shown in yellow box, will be committed by this year. We would like to discuss about this in Friday workshop. The application shown in the blue box are currently only available for Qt applications, but will be available for AGL Flutter applications by next year. We will continue to make contributions in bringing more advanced features of Unified HMI to AGL UCB. Please discuss in detail at tomorrow's workshop what we have committed to AGL UCB and the further future plan. Next section, I will provide how to use committed RBGPU features on AGL. Running RBGPU on AGL can be implemented in total 7 steps. Those steps contains from preparing your environment to rendering applications remotely. In this section, I will introduce the details of those 7 steps, focusing on differences from the AGL official documentations. Step 1, how to prepare your build environment necessary to run RBGPU on AGL and the flow of RBGPU commands. Currently, RBGPU supports 3 platforms x86, and Raspberry Pi 4, and AGL reference hardware. To use RBGPU, you have to prepare at least 2 of the above 3 platforms or Ubuntu PC, and use one at the sender and the other at the receiver. Applications are running on the sender and the application graphics are rendered in receivers. The sender and the receiver can be changed. Even if you don't have any ECU devices, if you only have an Ubuntu PC, you can easily use RBGPU by using Ubuntu PC and x86 emulation. All used platforms must be connected to the same network and accessible by IP address and connection port. The following figure is a flow of RBGPU commands. First, run RBGPU proxy command on the sender side and run RBGPU renderer command on the receiver side. Then, a virtual DRM device related Bataille GPU called CADX here is created and RBGPU is connected to the network. On the sender side, if Western or Wayland applications use this CAD device, called here CADX, those applications will be rendered in the receiver display. After the transfer, those applications displays on the receiver can be operated by touch and keyboard using your input device. Once the environment is ready, step 2, download the software necessary to run RBGPU on AGL. First, download the AGL software referring to downloading AGL software section in the AGL documentation shown in this URL. After that, you have to get the RBGPU recipes which was recently committed. RBGPU is in the meta AGL devel directory, but it is currently under review. So you need to switch Git branches with the following commands. After community review and integration, correct path of RBGPU will be updated in Unified HMI related section in AGL documentation we plan to add. The software will then be downloaded in the following configuration. In the figure, Meta RBGPU contains the recipes for RBGPU, and AGL RBGPU contains the features to use RBGPU on your build. Now, the software is downloaded. From step 3 to step 6, build and boot the AGL demo image. Step 3, initialize the environment variables and path settings in the build environment. If you add the AGL RBGPU feature when initialized, RBGPU is installed your build. Step 4, customize your build referring to AGL documentation. No specific operation is required here. Step 5, build your AGL image. Currently, RBGPU supports AGL demo platform and AGL image Western, etc. as AGL demo image. Here is the example command of building AGL demo platform. Step 6, once the build of AGL demo image is complete, deploy images on each platform you prepared, referring to the AGL documentations. Here is the URL of deploying AGL image on x86. Finally, in step 7, I will introduce how to use RBGPU commands. In this use case, Unified HMI render sample application running on sender on remote display on receiver. Here is an example of experiment with Ubuntu as the sender and AGL on each platform as a receiver. Please check our GitHub documentations on how to use RBGPU on Ubuntu. Only main commands are shown here, but several setting commands are required to run RBGPU. So please check our README documents in Meta RBGPU directory on how to use RBGPU on AGL in detail. First and second command, run RBGPU renderer on the receiver and run RBGPU proxy on the sender side. RBGPU proxy specify the window size of the application and the receiver's IP address and connection port. And RBGPU renderer specify application window size and connection port. When these commands are complete, a DRM device card X is created and RBGPU is connected to the networks. Okay. Third command, run Western applications with specifying the DRM device card X that's created by RBGPU. And the Western application is rendered in the receiver display. And fourth command, run Wayland application while Western application is being transferred. The Wayland application can be rendered in the receiver. Here, you can see that the GL Mark II application, which is not installed in AGL by default, is rendered in receiver display. While application graphic is rendered, application is still running on sender side. This concludes introductions how to use RBGPU on AGL. So if you are interested in Unified HMI, please try running and playing with it. Okay, final section. I will provide the future vision of Unified HMI. We are currently targeting the following 3 activities to achieve more flexible virtual display framework with Unified HMI. The first activity is expansion to support Flutter application as mentioned in our activities on AGL sessions. The second is enable application graphics to render in and out between AGL and other OS. Currently, remote transfer of application is possible only between AGL and Linux, but in the future, we would like to support transfer applications from AGL to Android and from Android to AGL. The third is extend Unified HMI to more media, such as audio and video. Currently, only graphics are supported by Unified HMI, but in the future, we would like to expand the media that can be controlled by Unified HMI. Okay, let's work together to create an ecosystem to enable new values of UI and UX in the multiple display environment with Unified HMI. Thank you very much for your listening. Thank you.